Right. So thank you for inviting me. It looks like it's going to be a wonderful conference. So as I think we probably all know in this audience, last spring, both the Washington and Cornell groups discovered fractional quantum anomalous Hall effect in twisted molybdenum telluride. And this was later followed up by FQAH observed in pentalayer graphene by Long's group at MIT. And so the anomalous here is simply referring to the fact that time reversal symmetry is broken spontaneously, so you don't need to apply a magnetic field. Otherwise, it's believed that these are essentially the same phases you would see in gallium arsenide. So here is a figure from the transport experiment from the Washington group, plotting the filling factor nu, or plotting the resistance as a function of nu. And you see here at 2/3 and 3/5, they have these little plateaus, which they show give very well quantized Hall resistance. But what I want to talk about today is instead of these incompressible states, the possibility of a compressible state seen here at nu equals 1/2. So there, this sort of linear RXY, as well as the small longitudinal resistance, are consistent with a possible anomalous composite Fermi liquid. So a composite Fermi liquid is a fractionalized, incompressible state of matter in which you have a Fermi C formed out of composite objects that are, the low energy degrees of freedom are composite fermions, which are essentially electron bound to 2 flux. And so this is a strongly correlated phase of matter. And I want to, talk about different ways this can be probed. In particular, I want to ask, given this whole new set, this sort of new experimental platform, what experiments are feasible now that maybe would have been sort of prohibitively difficult, before. And so in particular, I want to talk about universal features that can be determined by looking at tunneling junctions. So here I have a composite Fermi liquid integer quantum Hall interface, and here I'm showing composite Fermi liquid superconductor interface. And the superconductor interface is, what I'm, I guess, emphasizing by saying this sort of new platform, because obviously it's a lot easier to have a superconductor coexist with a composite Fermi liquid when the existence of this composite Fermi liquid is not predicated on applying a very strong magnetic field. That all said, otherwise, aside from making this sort of type of experiment more feasible, I will be treating everything identically to sort of the case you would get with a magnetic field. So if you were to apply, so in gallium arsenide, say. So just moving forward, I'm going to, as you see, I've already dropped the anomalous here, and we'll just be talking about composite Fermi liquids and fractional quantum Hall states. Okay, so my outline is I'm going to start by reviewing these quantum Hall states before talking about results that have already pre-existing results, looking at tunneling between fractional quantum Hall and integer quantum Hall and fractional quantum Hall and superconductor interfaces, before moving on to this composite Fermi liquid case. And this is work done in collaboration with my postdoc Chaojung Lee at UC Davis, as well as Hart Goldman at Minnesota, who should be here somewhere. Okay, so quantum Hall. As we know, we apply a out-of-plane magnetic field to a 2D electron gas. This quenches the magnetic field, resulting in these highly degenerate Landau levels. So just talking at a free electron level, when the filling factor nu has an integer value, so when the number of electrons divided by the flux quanta is an integer, that's when that means you have an integer number of Landau levels that are filled, And this results in a Hall conductivity that is nu, that integer, times e squared over h. So the Hall conductivity here is just, the current in the y direction divided by the potential difference in the, current in the x direction, potential in the y direction. Potential in the y direction. And experimentally, yeah, you see this sort of series of plateaus and resistance as you sort of tune the magnetic field. Okay, so more interesting, of course, is what happens when we add interactions. So here I've just sketched out a Coulomb interaction. And there you start seeing, quite similar physics, these same sort of plateaus, but now occurring at fractional fillings. So again, now this is the nu equals 1 plateau. So that's 1 fully filled Landau level, but now we have 2/3, 2/5, a large plateau at 1/3 that are being seen as well. And this is sort of provided your sample is sufficiently clean. And so these states of matter are fractionalized states. We can, the low energy degrees of freedom here are no longer properly electrons. We can kind of think about breaking up electron into 3 pieces, for instance, and the nu equals 1/3 state. So how do we explain this type of phenomena? Because obviously, via fractionalization, free electrons are not gonna cut it. So one way we can understand this is through what's called flux attachment. So what we do is we introduce an emergent gauge field, which I've called here alpha, and attach m of these alpha fluxes to each electron. Now, each flux quantum has an Aharonov-Bohm phase of -1. So if I have m being an odd number, and I look at this sort of what's enclosed in this black line here, well, with the electron and then an odd number of fluxes, we see that this thing here should behave as a boson statistically. And so this is sort of a bosonic description of the fractional quantum Hall state. We can then ask ourselves what is the effective magnetic field that this object sees, and it is the difference between the true magnetic field minus sort of the number of fluxes you've attached times the density. And so, if you're at the correct density and magnetic field, then this will cancel off completely. So when m is sort of provided, and so of course this would then be consistent with the fact that these fractional quantum Hall plateaus are typically seen with odd denominators, so like 1/3, 2/3, 3/5. This type of flux attachment can be formulated in terms of a Chern-Simons theory. So here I'm essentially just, if you take the equations of motion of this guy, what you wind up is getting this flux attachment. So I've just rewritten it. And if you take this theory here and then calculate the Hall conductivity, you will find that it does give that 1/m e squared over h that we were originally trying to explain. But we know that actually what's happening in these fractional quantum Hall systems is that Hall conductivity is being mediated by edge transport. So in the integer case, it's pretty, we even have like a nice semi-classical picture of skipping orbits around the edge. This is sort of what's, I guess it's going this way. What is mediating this Hall conductivity? We obviously can't write down something quite so simple for the fractional case. And in order to understand the fractional case, it's actually better to consider instead a dual Chern-Simons picture to the one that I just gave. So instead of these sort of this gauge field alpha with this sort of fractional level 1 over m here, we go to a description where I have a different gauge field m with a different gauge field whose Chern-Simons term has an integer value on top. So this is better in some ways. Also important though here is that this gauge field A now couples to the external, the sort of physical external field through also through a Chern-Simons coupling, whereas here this sort of alpha coupled directly to matter in the same way that that big A would. Okay, so when we start with this theory and then we add an edge, you'll actually find that it is no longer gauge invariant on that boundary. And we can understand gauge invariance as kind of removing degrees of freedom from our theory. We, want to write everything down locally, but to do so we have to add in degrees of freedom that aren't actually there. And so, the absence of gauge invariance on the boundary means that we have physical propagating degrees of freedom now. And these take the form of some chiral bosons. So you can write down the theory in terms of this phi here with this integer m, which is essentially telling us what how much charge is sort of actually being transported along the edge, which is again what gives us that conductance. All right, so at this point, having described, flux attachment and the edge theory, I now want to move on to talking about the tunneling and how you can describe this type, what the tunneling, point contact tunneling would be between a fractional quantum Hall and an integer quantum Hall, just based on dimensional analysis. So we write the electron on the edge in terms of that phi, that chiral boson, and it's a vertex operator e to the I m. If you look at the Green's function then that you get, it sort of goes as 1 over x plus vt to the power of m, from which we would conclude that, the scaling dimension of the electron operator is m over 2 in this sort of nu equals 1 over m fractional quantum Hall state. So if we want to look at tunneling then between these 2 points at x equals 0, the action we would write down would have this electron, hopping the electron on the fractional quantum Hall state in terms of the vertex operator, just, becoming the actual physical electron that, is propagating around the integer quantum Hall boundary. So this has scaling dimension m over 2, dimension 1/2. From which we would then conclude that the tunneling coupling has to have scaling dimension 1 minus m over 2. And so, provided m is greater than 1, so we actually have a fractional quantum Hall state, that means that this tunneling is irrelevant in the renormalization group sense. So this is a weak perturbation that we don't need to worry about actually modifying the theory at low energies. It's going to, at 0 energy, flow to 0. But then that means that sort of when we add, either a non-zero bias, so a voltage difference across here, or else we have a finite temperature, that means that we expect, the result to be universal. So we know that the conductance, just from Fermi's Goldman rule, should go as gamma squared, gamma being this tunneling coefficient here. And so then just from dimensional analysis, we know that G here has dimension, 0. We know what the dimension of gamma is, so what is going to be the coefficient alpha? And it turns out it's just m minus 1. So you can show that conductance, scales as v to the m minus 1 or t to the m minus 1. Can this actually, okay, so this is like an experimental prediction, essentially. Can such an experiment actually be performed? And the answer is yes. So back in the 90s on gallium arsenide, Chang et al. Sort of grew samples with, some barrier, and from that they were able to get, to find that the current had a, power law form as a function of the bias that was being applied. So this is for nu equals 1/3. So did the coefficient actually match what they expected? Well, they found that 2.7 instead of 1/3. And, it's believed that there's why they don't get the correct, quote unquote, correct answer, the predicted answer, could be because of what's called aggregate construction or disorder. But more recently, at UCSB, Andrea's group, performed, I guess, a similar set of experiments, again with integer quantum Hall to 1/3, and now they're using this point contact geometry that I'm really focusing on. And so here they measure the conductance, and they find that G goes as V squared. So the actual exponent that they find is sort of 2 plus minus 0.06. So very beautiful, accurate measurement of this sort of Luttinger parameter. So this is sort of proving that sort of scaling analysis that I showed a few slides ago. Okay. So now let's consider what can be done with a superconductor. So, as I said, this is definitely more feasible that we actually have these anomalous Hall states, so we don't need to worry about killing our superconductor. I mean, you could still consider doing this with an actual fractional quantum Hall state as opposed to fractional quantum anomalous Hall, but okay. So the first problem, right, and I guess I should say I'm going to just assume S-wave spin singlet superconductor. Right, so the first problem is that I have been so far implicitly assuming that I only have one flavor, say spin up, realized in my fractional quantum Hall state. And, that obviously makes tunneling into this singlet object, quite a bit more difficult. And so I'm just going to start by writing down sort of a general Hamiltonian here, where I have Cooper pair tunneling. So this is sort of, these is spin up and spin down on the fractional quantum Hall side. And then this is the pairing operator, the condensate on the superconducting side. And then I'm also going to need to have some sort of spin flip process. I'm going to break the spin symmetry. This could be done, for instance, or this could exist, for instance, because of spin orbit coupling, which is of course present in TMDs. In TMDs, you would also need to worry about valley, but that shouldn't be a problem either, really. And so, so we're going to start with this sort of perturbative Hamiltonian, and of course, but we really want to get rid of, these down operators, because like I said, we really ultimately want to be projecting onto the ground state of this left-hand side where we only have spin up being realized. So it's fractional quantum Hall state that is polarized. So if we just do perturbation theory, what we find is something of this form here, where this sort of hopping now Txx prime is proportional to both the spin flip as well as that Cooper pair hopping, divided, of course, by some gap. Now, and this, of course, now breaks the spin symmetry, which was necessary. You'll also notice that I've been very, whereas previously I wanted to just, from the get-go set x equals to 0. Obviously, I've avoided doing that in this case because Pauli exclusion will just kill everything. But I can still simplify this type of this tunneling term by noting that this pair correlation here will be very quickly suppressed once the difference between x and x prime is greater than the correlation length of the superconductor here on the right-hand side. And so I'm just going to essentially set the difference to that correlation length. And then follow up by simplifying even further by expanding in that correlation length. So giving something here where I have, psi dagger dx psi dagger, now at x equals 0. Okay, so this is just symmetry-wise kind of the simplest thing you could write down that would be non-zero for a tunneling operator. And of course, I've sort of hidden the condensate into this now parameter gamma, which I guess also includes the correlation length here too. Okay, but so long as we've gotten to this tunneling, we've gone through this whole process of arriving at what I've now just called H10. We can do the same scaling analysis game. So again, we have our chiral boson edge theory, which is telling us that the electron on the fractional column Hall side has scaling dimension m/2, which then means that this operator here is scaling dimension m+1, because I have this dx here, which gives me a scaling dimension of gamma, and in turn I find that g scales as v to the 2m or t to the 2m at 0 temperature or 0 bias, respectively. I guess I should say that this was done by Matthew Fisher back in the 90s. Here as well. Okay, so as far as I know, this hasn't actually been studied, in part because, as we say, it's difficult. But taking this as inspiration, let's now consider the composite Fermi liquid. So what can these point contact experiments tell us? So I'm going to kind of give the answer away, so hopefully you guys will still pay attention. For the composite Fermi liquid integer quantum Hall interface, you find that G goes as the bias v squared. So this is actually means that there's really no turns out there's really no information about the non-Fermi liquid nature of the left-hand side here. But when you do look at the superconductor interface, we find that it goes as v plus certain dimensions here that depend on both the self-energy as well as the anomalous dimension of the pairing operator. So why don't I try to explain that? So to start with, let's talk about how we describe the composite Fermi liquid. So again, flux attachment is the way to go. So now we're at nu equals 1/2. So instead of adding an odd number of fluxes to our electrons, we're going to add an even number. And again, that means that because each of these fluxes has a Aharonov-Bohm phase -1, this object here in black is no longer a composite boson, but a composite fermion. So at nu equals 1/2 on average, the mean field level, we find that again this composite fermion doesn't see any magnetic field. But because it's a fermion, what that means is that it's going to want to form a Fermi sea. And so you can get as first written down by Helper and Lee Reed, you get an action sort of this form where this little a here is that sort of emergent gauge field that that is sort of giving this sort of emergent flux that we've attached. Okay, but like I wanted to talk about a dual description for the for the composite, in order to talk about the edge theory, the same is sort of true here. It's, in particular, it's convenient to look at a parton approach. So we start by rewriting our physical electron in terms of a charged boson, and then what I'm going to call the composite fermion. This type of rewriting, has a redundancy under of it, so it does, from the get-go imply that that this is a gauge theory, particularly with a gauge field, what I'm going to call little a mu. Then the next step is, we don't actually want to what do these bosons do? Well, they carry all of the charge, and so they're the ones that see that there is this magnetic field has been applied, and that they're at half filling. And so they just form an integer quantum Hall state at nu equals 1/2. So they form a bosonic Laughlin state at nu equals 1/2. And so in total, then, we have our composite fermions, sort of kinetic term here. And then I have this alpha, which is, the same, that same term I had, just, by itself would describe the 1/2 Laughlin state. And then it's not completely independent, of course, from the fermions, but couples to that emergent gauge field, little a, as well as what I've called a he here, which is the external field, the applied field, but as it deviates away from nu equals 1/2. So if you're right at nu equals 1/2, then this yellow a here vanishes, 0 by definition. Okay, so this is a strongly correlated theory, and so we can try to understand it to the best of our ability, particularly using RPA. So if you do RPA calculations, you find that the self-energy of that's not very good. Self-energy is takes this form, the absolute value of omega to 2/3 minus eta c, where eta c here is the exponent for the Coulomb interaction. I have, of course, hidden additional interactions in these dots. For instance, that Coulomb interaction. I say Coulomb. Now, if eta c is 1, that would be the proper long-range Coulomb. I'm actually going to, for this talk, assume that we actually have a local interaction, so that would be eta c equals 0, in which case we get this factor of 2/3. So I'm going to, our Green's function takes this form in the RPA approximation with y equals 2/3. In particular, then, 2/3, that is, to my understanding, less than 1. Which means that at low energies, this term here is sort of negligible. So you can just sort of drop it out and work with this in the scaling limit. This, of course, also implies that this type of existence of this self-energy, means there are no quasi-particles. This is a non-Fermi liquid state, even though we're still talking about having Fermi surfaces. Okay, to get the boundary theory, this is actually quite important and probably shouldn't be rushed, but here we are. Again, I wrote down, I said we can just sort of think about this alpha d alpha here as what you would get just on its own from the, having just the nu equals half Laughlin state. And so that nu equals half Laughlin state, on its own also gives you sort of a propagating chiral boson, which I'll probably just keep calling the semyon. So again, it's the same with level 2 now up top here, okay? But, before we were talking about these incompressible fractional quantum Hall states, you didn't really need to worry about whether or not this edge mode was going to, you didn't need to worry about anything in the bulk, messing up with the existence of the edge mode because there wasn't anything in the bulk. Obviously now in the bulk we have a Fermi C. And so is this boundary mode phi, is it stable? Well, first of all, it cannot couple directly to the bulk fermions, right? So this was only coming from, this phi here comes from this alpha, and alpha doesn't couple anywhere to the actual fermion degrees of freedom themselves. It only couples to the fermions via the emergent gauge field little a here. Okay, so how can it couple to that little a? Well, because of momentum conservation, it can only couple to the emergent photon in this form. So partial x of phi, x being this direction, and partial x of a transverse. So particular a y in order for this to not be 0. I am assuming here Coulomb gauge. So if we integrate little a t out, a transverse out, what we find is something of this form, where this is the propagator of the gauge field. But what's mostly important here is that I get this p to the 4 here. So, unless this propagator is incredibly singular, which it isn't, this is going to be an irrelevant, perturbation on top of the theory. So this, which is to say that, the interaction between the bulk degrees of freedom, so the little gauge field A, and phi, is irrelevant. So we have a stable boundary semyon in addition to our bulk degrees of freedom here. Okay, so from that we write down our tunneling Hamiltonian now as we would for the composite Fermi liquid to integer quantum Hall case. Yeah. And taking into account that, our physical electron has has to be rewritten in terms of this boson, which on the boundary then is again a vertex operator, times our composite fermion. Okay, so, tunneling, this is sort of the left-hand side, the composite Fermi, the electron, as per the composite Fermi liquid degrees of freedom, and this is just, the electron that is going around the edge of the integer quantum Hall state. Unfortunately here, scaling, you can do scaling analyses, but they aren't as trustworthy, particular because KF here, the Fermi wave vector is an additional scale that enters in and complicates the analysis. The upshot of it being that you have to be a little bit more honest with the calculation that you do in order to get what the conductance is. And it sort of involves some convolution that I've very roughly sketched out here. Okay, but if you do that, what you find is that it just goes as v squared. And in particular, it doesn't actually depend at all on the fact that we have this self-energy that went as omega to the y. It doesn't care that there aren't actually, quasi-particles in the system. And we can try to understand this mostly just based on the fact that this tunneling, that the tunneling here, we expect it to be proportional to the density of states. And the density of states, doesn't really care about this Fermi liquid signature. We can, maybe understand this as that at low energies, not even the momentum k matters relative to omega. But yeah, that's sort of I guess, yeah, the heuristic way of understanding it is that it, this just depends on the density of states. This is different for the superconducting composite Fermi liquid tunneling, where now, in terms of electron operators, it takes this form where I have this derivative here. And so what I now want to do I still again have to do the proper calculation. What I find is that I have to calculate this correlation function with this derivative. And so that essentially annihilates, in some sense, that leading order contribution that didn't care about this non-Fermi liquid contribution, and we wind up that's something that scales as v to the 4 plus y plus an additional, actually, anomalous dimension that comes about from vertex corrections, which has not actually been finalized, the value. Okay, so in summary, I've looked at weak tunneling between quantum Hall states, metals, and superconductivity. I've shown that this can reveal important information on the strongly correlated nature of these systems. Non-Fermi liquid character of the composite Fermi liquid can be observed through tunneling with a superconductor, but not with an integer quantum Hall state. And then, yeah, future works, other types of junctions, disorder, potentially instanton effects, long range, Coulomb. Yeah, thank you very much.
Okay, Chenke.
Thank you for the nice talk. So I just wonder, it seems like you used the Green's function of the composite fermion side in the bulk to calculate the tunneling, but I think once you use the scaling dimension, the scaling behavior of the psi as the boundary to calculate the tunneling. And actually for a gapless field in the bulk, the scaling as the boundary can be very different because of boundary condition. That's how we get all the boundary CFT and all this stuff. I mean, the scaling dimension can be extremely different from the bulk. I mean, for example, that Y can be very different at the boundary from the bulk because the dynamics of the gauge field can be very different at the boundary from the bulk.
So we've looked at the gauge field in a fair bit of detail, and that isn't an issue, the way that the boundary theory behaves, at least, assuming the most natural boundary conditions.
What is the most natural boundary condition then? It needs to be Dirichlet, I assume, but
the what?
The Dirichlet boundary condition.
Yeah.
Yes, but then you evaluate that. You have to reevaluate the self-energy for the Fermi as the boundary, right? It's still the same Y, or? Okay, then what about the psi? The psi itself should also have a scaling dimension. I mean, should also have the boundary condition as the boundary. You mean at the boundary, the Y is still the same as the bulk? Okay. Okay, that's a bit surprising, but okay.
So I have a very naive question. So when you count the scaling dimensions, why don't you consider time in the action? Usually we say time is another dimension.
What? Yeah.
So if you show the action that you wrote, the action of the coupling.
Oh, was I just?
Yeah, for maybe it's clear if you show the very beginning.
If there's a mistake, that's just going to be a typo, not that I didn't include
next
time.
Next page. So yeah, my point is, why don't you consider time when you count the scaling dimension?
I do. I don't know what.
Next page, maybe. Here, yeah. So what do you think? So,
why are we
the action has dt integral, so t has dimension. That's my point.
Yeah, so that's that. We have
That's you has 1 minus m. Oh,
yeah.
sorry.
So like I said,
sorry.
Yeah. This isn't. Just to be clear, this isn't my result. This is from Shogunlin. Okay. I don't.
Hi, thanks for the very, very nice talk. I have two related questions. So one way I like to think about composite Fermi liquids is the m to infinity limit of the Jane sequence.
Okay.
So if for each of the Jane sequence states, I can probably do the Luttinger liquid calculations on its edge. If I do that, can I reproduce the same results in this sense? No, yeah.
I mean, probably. Okay. Because for each step in the sequence, you have a different operator that you're considering, right?
I agree.
And you're approaching kind of like a continuum limit of operators. So I don't know. Maybe it doesn't sound easy, but it'd be interesting if you could do that.
Thank you. Another related question is, it seems that you have shown that in the composite Fermi liquid, there is a decoupled semyon, almost decoupled semyon edge mode. I'm wondering if this is, I mean, this is already very surprising to me. And I'm wondering if that has any experimental consequences on its own.
Yeah, probably. I should say that I think was first. Where am I going? Where am I going? That was probably first said by Shatov, Levatov, and Halperin in '98, and then later by Barkashli and Mulligan and Fisher in 2015.
Cool. Thank you.
So I have a technical question. So your coupling of the semyon mode with bulk degrees of freedom, you included the gauge field coupling.
Oh, no.
I guess that's this. Now, in principle,
Please continue.
you need to plug it in.
Yeah. It's not funny, guys.
So in principle, there's also a coupling to the fermion current, the composite fermion current, right? Fermion bilinear.
To the fermion what? To the
current of composite fermions, right? So I don't know, is that an independent coupling or it's the same one in disguise?
So you can think about this coupling as being coupling to the density through the flux attachment condition.
Yeah, okay.
And then kind of assuming that this is the only propagating piece, that the sort of time component, the scalar part, has been screened as well.
The fermion bilinear, is that?
Yeah, so this would be the fermion by the Seidegger, or Seidegger psi is this, if you from flux detachment. But probably you're right that it would be good to do this calculation entirely in that language as well, instead of just substituting the flux attachment. But yes, but that is kind of the same, if you believe that.
Okay, so I have two questions. So one question is about connection with the quantum Hall effect at half filling factor. So you can see the tunneling between actual superconductor and a Fermi liquid of composite fermions, which is something that corresponds to a half integer filling factor. But one could consider perhaps a system where you just have the same filling factor on both sides. One is some sort of a composite fermion superconductor that is half integer quantum Hall effect, and the other is composite fermi liquid. So what would your prediction for that be? So is it possible to extrapolate from your calculations? That's my first question.
You're saying like essentially a Moiré composite fermion?
For example, yes, you tunnel from fermi liquid to Moiré.
Yeah, we haven't, that was like the original, like what would, that was the original question. And we haven't quite gotten to there yet. But yeah, I don't think we have a good enough understanding of the scaling and how the intricacies of that work to just sort of give you an answer. But yeah, it's a...
And my other question is related to the very beginning of your talk, where you showed some experimental data and, among other things, mentioned that at the filling factor 1/3, there is some set of experiments that give some 10% or even better accuracy for the tunneling exponent. But of course, for all other filling factors, we have terribly poor agreement between theory and experiment, no agreement at all. And even at 1/3, these experiments performed by Albert Chang from the very beginning had a very strange feature, which I don't believe is quite understood, that if you change the filling factor slightly, even on the 1/3 plateau, this critical exponent actually changes. It just shows a more very consistent change in a very broad range of filling factors instead of showing plateaus. And I wonder what happens in your case. You obviously don't have a quantized plateau because you don't have a gap state, but nevertheless, is it possible to get some idea of what happens when you change the filling factor slightly from your picture?
Well, so I don't know what's happening in this experiment. I think there's probably a lot of non-universal physics happening here. And that was why it's sort of nice that these more recent experiments do find the scaling. But you're just asking how we expect if we have, okay, so yeah, we would have to consider, you're saying if we also essentially dope this composite Fermi liquid side, how will that enter in here? And I don't know, is sort of the answer. I mean, I'm assuming that temperature scales the same way, but yeah,
You don't have an expectation that this is universal exponent. So that's my question. Change slightly the filling factor. Would this exponent you have remain constant, or would it change? What's your expectation?
I mean, I expect they would change, yes. Mm-hmm. But they might change in like or would the exponent, I don't know if it's correct to say that the exponents themselves would actually change. Like especially this one, I don't know if this one would change. This one seems very agnostic to sort of the half-filling condition. But you would definitely get a more complicated functional form that I don't have a good enough intuition, really, to give you an answer. Sorry.
Thank you.
Yeah, okay. There's two final quick questions.
Yes, thank you, Alex. I had a question about your is the chiral boson stable slide. You can flip back to that one. So since we have this gapless fermion mode in the bulk, I can imagine if I have multiple edges generating a density-density interaction between different edges mediated by the gapless degrees of freedom in the bulk. Does this kind of same argument say that that's not going to be relevant as well, or is that different?
Say that what?
Would this kind of similar argument that you've sketched out here for a single edge also indicate that there's no, say, changing of the boson, scaling dimension if we have long-range interactions between different edges mediated by the composite fermions?
No, I mean, if you have multiple edges, just even for fractional quantum Hall with sort of a incompressible bulk, then the situation also becomes more complicated. And so if you have multiple edges, then I think you would again need to reevaluate what is happening in more detail. And I mean, this is why, like, one of the explanations for Chang's results was that there was edge reconstruction, because that definitely, the presence of, additional integer quantum Hall edges sort of changes the answer.
Okay, last question.
Hi, so great talk. So can I just have a question about the tunneling term. It was psi, dagger, partial, psi, they were both up. So in TMDs, I think,
Where am I?
well, there was
like the
some
last one, I think.
partial, it was psi, dagger, partial, x, psi, dagger up. Okay, right. So that's, if I was to apply it to TMDs, they would have the same momentum because they would be the same value. So that wouldn't be a momentum zero term, right? Is that?
Yes, yeah.
So would it still exist, is my question.
Well, I mean, it's definitely not translationally symmetric either. So you would be assuming that the boundary is sharp enough, which you want it to be sharp, that inter-valley scattering is allowed.
But if I do second order, I guess you obtain from second order perturbation.
Yeah,
If I do second order perturbation TMDs and I have translation invariance, I wouldn't obtain this term, right?
Yeah.
Okay, thanks.
Okay, so let's thank Alex again and move to our next speaker.